Okay, so welcome to the 21st video in the discrete structures series, and this video is going to be a continuation of our last video of propositional logic. In the last video, we looked into the basics of propositional logic, the basic connectives and or, the negation operator, the XOR, and also looked at the idea of truth tables. We'll resume here with a look at implications, and we'll look at common accidents and fallacies that we make on implications. Next, we'll have a look at the biconditional implication. We'll then follow that up with three derivatives from implications, and these are converses, inverses, and contrapositives. And then we'll close the segment with a look into a very important topic, and that is about the applications of propositional calculus. And there are two applications that are relevant to our course. One is the translation of English sentences, and this idea of system consistency verification, which is basically asking the question, can a set of propositions even coexist? Okay, so that is the overview. Let's get started with the first topic of implications. So an implication is anything that defines a cause and effect phenomenon. Okay, so if in nature something causes something else to happen, we use this notation, and this is called implication. This is most commonly read as P implies Q, and this statement is basically a guarantee that if P happens, Q is bound to happen. But the most common mistakes made in logic are inside of implications. So there are a couple of things that we'll see. First, you want to be aware of these other alternative notations for an implication. So these are really common ones and should be easy to understand. And there is one that says P only if Q. Okay, so this is also the same as P implies Q, and this could be a little bit confusing. To see why this is the same as this, let's think of what this means. P implies Q means every time P has happened, Q has happened. Okay. So you will not find any situation where P has occurred and Q has not occurred. Because by definition, as soon as P happens, the implication causes Q to happen. And because every happening of P can guarantee a happening of Q, you will see each and every existence of P coupled to a corresponding existence of Q. Therefore, we are precisely able to write P only if Q. So let me draw a truth table for two propositions, P and Q. You should think of P implies Q as a promise. It is a promise made by P that every time P happens, Q happens. But the point is, when P does not happen, you are not allowed to make any judgments about this implication. Okay, so let's say your teacher makes this statement. If you get 100%, I'll give an A grade. So you getting 100%, let's call that H, implies that you get an A grade. Let me just call that G. Like I mentioned earlier, we should think of this as a promise made by the teacher that if you get 100%, you are bound to get an A grade. Maybe some student did not get 100%. Maybe they only got 98%, but they had excellent laboratory report and performance and also good attendance. So the teacher decided to give them an A grade anyway. So in the case when you do not get 100%, it is up to the teacher to decide. And whatever choice he makes should be considered valid. You should only feel betrayed if you get 100%, but the teacher still did not give you an A grade. And that would be the only situation when the promise would be broken. Okay, so when we are looking at P implies Q, if my original premise P is false, I sort of cannot blame the implication. Okay, therefore I have to consider it true because I don't have enough information to judge. And I can only blame the implication and call it false if P happens and Q does not happen. So this one situation here where P is true and Q is false is the only situation where the implication would be false. In these two cases, you did not get 100%. So whatever the teacher did is a right choice. You have to call it true. But in this case, you got 100% but still did not get an A grade. That means the promise was broken and the implication results to a false. And in this case, you got 100% and you indeed got an A grade. So the implication is still true. So the reasoning behind why the false implies true is discussed differently in many books. But I think this is one pretty easy way to think about it. And one last really important fact before we leave the topic of implications is that an implication P implies Q is logically equivalent to not P or Q. And there are two ways to see this. You can see P is false here, and whenever P is false here, the implication is automatically true. So not P is covering for these two possibilities. And then this or Q term ensures to cover this space. And this is the only row where not P or Q is false. And I think some of you would have guessed, you could also generate the same expression using a two variable Carnot map on this table. But I think a more satisfying way to think about it is to consider the idea of promises that we discussed earlier. So this not P suggests that P did not happen at all. And I know that this is one of the cases where my implication is automatically true because the premise has not been met, the implication is automatically true. And there is another criteria for the implication to be true, and that is whenever the implied proposition happens to be true. That means if the teacher gave you an A grade anyway, In that case, I don't even have to look at the premise to see whether it was true or false. And anytime you need to simplify a compound proposition by using laws of Boolean algebra, you'll need to represent an implication in this form. And one last way to verify this is simply to draw not P here, and then you can draw Q, and then you can take the OR of two things and see if they match with these values. So you can construct the truth table to verify if you're interested, but I'll just move into the next topic now. Next, we'll be looking into the ideas of the biconditional. A biconditional is also called a double implication. And for two propositions, let's say P and Q, it is denoted using this symbol. So with a bidirectional arrow. And this simply means that P and Q always happen in pairs. So the happening of P will guarantee the happening of Q and vice versa. And a bidirectional implication like this is equivalent to this expression. P implies Q and Q implies P. So let me quickly draw the truth table here. So the definition is enough. This is quite simple. Either both should happen or both should not. So this is a correct criteria. I'm labeling true because both did not happen here, and that is allowed. These two cases will be false because in a double implication, both should happen in pairs or both should not happen. So this should also be true. And earlier we saw that P implies Q would be written as not P or Q. And similarly, if a bidirectional is given, P bidirectional Q. So this is quite simple. Either PQ should be true, both should happen, or both should not happen. I did not put any operation here, but you should consider this to be a conjunction. And this simply states that both things happened, and this states both things didn't happen. And that are the two possibilities for a biconditional. Okay, so the next topic that we're going to look at is going to be a derivative of implications, and that is converse, inverse, and contrapositive. So we looked at the truth table of the implication P and Q. We also looked at P and Q was equivalent to not P or Q. So given this implication P and Q, there are a couple of other implications that we are interested in. So the first one is the converse. And the converse of an implication is simply a new implication obtained by substituting the rules of the propositions. So from P implies Q, if I write Q implies P, this is the converse of the statement P implies Q. And before discussing more on this, let me mention the other ones. The inverse is the new implication formed by inverting each proposition. So the inverse would be not P implies not Q. And so for the contrapositive, we do both. We flip and take the inverse. So the contrapositive of P implies Q would be not Q implies not P. So I think you would be easily able to construct truth tables for these types of derivatives, given the original implication. So I will not be going into the truth tables, but there is one point that is really important to understand, and that is how we define the relationship between these statements. So you should note that the original statement is always equivalent to its contrapositive, and similarly the converse and inverse are equivalent to each other. And obviously by equivalent, I don't mean that they are the same thing, but I mean that they have the same truth values. If you have proven an implication, you have automatically proven its contrapositive. Similarly, if you have proven the converse of a statement, you have automatically proven the inverse of it. However, the original statement being true does not automatically cause the converse to be true or the inverse to be true, but it does guarantee that the contrapositive is true. And let me show you an example to demonstrate that bucket will fill if it rains. So if I try to break this down as an implication, let us denote R as the proposition that it will rain and F as the proposition that the bucket will fill. And then this statement is saying if it rains, that bucket will fill. Okay, so then R would imply a F. And now we'll try to make sense of the converse, inverse, and contrapositive in this context of example. So the first thing that I want you to notice is about the contrapositive. The contrapositive is not F implies not R. And this is equivalent to saying the bucket didn't fill implies it didn't rain. And you should be able to see why this is correct, because my original statement has promised that the bucket will fill if it rains. And if I can observe that the bucket didn't fill, I can definitely conclude that it didn't rain. And it's very important to understand that there could be other reasons for the bucket to fill. For example, I might decide to fill it with a pipe, or maybe the bucket filled because it got into a pond. And all of these will cause the bucket to fill. Pipe implies fill, as well as the pond implies fill. But if I know that the bucket did not fill, I can guarantee that none of the causes of the bucket being filled have occurred. Nobody has put a pipe, the bucket has not fallen into a pond, and it has not rained. Okay, the fact that the bucket did not fill denies all of the possibilities that could fill the bucket. So you'll see that my original statement was rain implies fill, but being dropped into a pond also implies fill. Therefore, not being filled will imply that it did not rain, and it will also simultaneously imply that it did not fall into a pond. So this is extremely important to know. Whenever P implies Q is true, or whatever truth value this has, not Q implies not P will have the same truth value. But if I just consider the inverse, not P implies not Q, Well, it is like saying that the bucket will not fill if it doesn't rain. And that is false because it could get filled by other reasons, including our pipe and the pond. And therefore we say that the original statement and contrapositive are always logically equivalent, but the original statement and its converse is not. But then it's easy to see that the converse is also the contrapositive of the inverse, because it is the same relationship as this and this, just Q and P have changed their roles. So if I take the contrapositive of the converse, I get the inverse. And one last point, there could be situations where the original statement as well as its inverse is true. And those type of statements are the biconditionals. Okay, so next we'll look into a couple of applications of propositional logic. So let's look at translation of English sentences, and we use this to translate common language English sentences into propositional logic formats. And that involves finding the different propositions involved in the sentences and finding the logical connectives used in those sentences. So let us see a couple of quick examples. You are allowed free entry only if you are a student or you are not a foreigner. Okay, so I think it's worth understanding that this by itself is a proposition. Okay, so I could call this whole thing P and be done. But that doesn't help much when I'm trying to reason with it or break its components. So what we want to do for examples like this is to find the basic or simple propositions that are composing this compound proposition. And then we'll find the necessary connectives and join them together. So let me call this statement E. You are allowed free entry. I want to call this E. Obviously, you might want to do this a little bit more formally. You are a student. Let's conveniently call that S. And you'd want to mention you are a foreigner as F. I only highlighted this, but the proposition you want to assign to this is going to be you are a foreigner. Okay, and that's going to be F. So now let's start constructing this. You are a student appears in its normal form. Let's begin by writing S. And I have not a foreigner. Let me write F and then complement it. And I'm mentioning or in this situation. So let me put a logical or. And there's an implication relationship between this expression and free entry, but I want you to decide which way it is. And it should be quite easy. This implies E. Okay, so if any of these criteria is met, you are allowed free entry. Okay, and this was a relatively easy topic, just formalizing these sentences using logical connectives. Next, we are going to look into another use case of propositional logic, and that is called consistency verification. So this is also quite simple. Let's consider this example. The TV has turned on. There is no power in the house. So if you look into these two sentences, they are not consistent, because in order for the TV to be on, there must be power at the house. So whenever we are given a list of sentences like this, we often need to find if they are consistent, meaning if there is at least one possibility of them being true. It is just the question, can those sentences or can those statements coexist at once? Is it possible to make a consistent set of assumptions that do not contradict with any of the given statements? So that is the goal here. So let's look at an example of consistency verification. I'll write 3 compound propositions here. Okay, before assigning any proposition to any variable and looking at this formally, I just want to look into these sentences and see if we can resolve them. So it helps to begin looking here. This one says that the message is not stored. And then once we go into this one, it says message is stored or forwarded. So stored or forwarded, one of them must be true. And this one says that the message is not stored. So the message must have been forwarded. So by looking into these two statements, I can say that the message was not stored and the message was forwarded. So this is false and this is true. And what is this statement really doing? It is just declaring an implication. If message is stored, it is forwarded. It means that stored would imply forwarded. And in this particular case, we are looking at the value false implies true. And we just looked into the discussion of implication that false implies true would actually be considered true. So these 3 sentences are actually consistent. And if you are not quite satisfied, it's probably because of this. But you should understand that this implication would only have been false if the message were stored but not forwarded. And that situation of being stored and not forwarded is not given in any of these sentences. So this is actually consistent. But let us add a 4th sentence here. So if I include this message is not forwarded, then in that case, these 4 sentences would not be consistent. Because this one mentions that the message is not stored. And from that, I conclude that it must have been forwarded. But this one contradicts with that assumption. So no matter what truth values I use for stored and forwarded, I cannot get all of them to be true. Okay, so logically speaking, checking for consistency is checking if at least some set of inputs cause this to be true, all of them. And therefore the formal way to do this would be as follows. So you would obviously start by denoting these propositions with variables. So message is stored, let me call that S. Forwarded, let me call that F. And then I have my propositions here. Message is stored or forwarded would just be S or F. Message is not stored would just be not S. And if you consider 3, message is stored, it is forwarded. That means Stored would imply forwarded, and the fourth one suggests that the message is not forwarded. You could simply do not F. And if you really want to resolve this without putting any thought, what you want to do is construct a truth table. You want to combine all of these expressions using an and so my expression would be S or F and not S and this and this. Okay, and then I'll calculate each of them component wise and do an and look into a truth table. And if I can see in the truth table that at least one set of rows is causing a true output, I could consider that these messages are consistent. And instead of drawing the truth table, once you take the AND of all of these operations, you could try to simplify them algebraically. That is using the laws of Boolean algebra. And when you do that, all you want to do is to avoid a contradiction. You don't want to reach a situation or an expression that is always false. But I won't be going into the simplification of truth tables and algebraic simplification now, because we'll be going through those things in the upcoming videos anyway. And here I'm just bringing this up as an application of propositional logic. But for your purposes, I think if you get questions of this nature, you should be able to reason just using common language and argue whether the system of propositions is consistent or inconsistent based on your observations. Okay, so I'll just close the topics for this video now. In the next video, we'll be looking at propositional equivalences, predicates, and quantifiers. So I'll see you guys in the next one with those topics, and until then, have a good day and bye.